Carboxylic acids are a really important functional group biologically because, as we are going to see in the next chapter, a variety of these play key roles in fats and lipids, such as many of the compounds listed here that have long alkyl chains shown in gray representing carbons, and then the carboxy group shown here at this end of the molecule representing the carbonyl group with the oxygen in red and the carbon in gray, and hydrogen shown in white. So as we begin to set the stage for learning about fats and lipids, we need to talk about some of the key reactions that carboxylic acids can undergo. And one of the key properties of carboxylic acids that we need to focus on is the fact that, unlike most organic molecules, carboxylic acids, as the name acid implies, have a readily ionizable functional group, and that's COOH. In other words, this proton here, the COOH proton, can readily be lost when reacting with a base. So we need to talk about that a bit more because there are certainly implications of that, meaning that when a carboxylic acid molecule is in different environments within the body or another environment, what will happen is that if the pH is relatively low, the molecule will retain its proton. On the other hand, if the conditions shift so that the conditions are increasingly basic in nature, that proton will be lost. So let's take a closer look. Carboxylic acids are relatively acidic functional groups. Of the functional groups that we've looked at, they are the most acidic that we have encountered to date, and in fact, the most acidic of the traditional functional groups that we will focus on, period. Carboxylic acids have a pKa value of approximately 4 for a typical carboxylic acid. That varies a bit based on what other functional groups are present in the molecule, but generally, a safe assumption is that the pKa is approximately 4. So what implications does that have for us? That means, with the pKa is 4, if the pH of the solution, such as the physiological condition that the carboxylic acid is put in, is greater than 4, then the proton from the COOH will be predominantly lost. In other words, the COOH will become the carboxylate salt, COO-. On the other hand, if the pH is less than 4, the COOH will remain as COOH. So the COOH is unchanged. So in other words, what this is telling us is that at a neutral pH of 7, what's going to happen is that carboxylic acids are predominantly found as the COO- form, because of the fact that the reaction is an equilibrium reaction. Specifically, the reaction that we are talking about is the reaction whereby we have a carboxylic acid functional group, such as this, and I'll draw that OH bond to the proton explicitly here, and I'll show my lone pair electrons. When this reacts with a base, which I will abbreviate as B, with a lone pair of electrons to allow it to act as a base, and a negative formal charge on that, an equilibrium will form in reaction with that base, where the base can come over here, grab a proton from the carboxylic acid, and we show that with this electron pushing arrow where we begin with the electrons at the beginning of the arrow, and then the head of the arrow targets that proton, indicating that the base is attacking the proton, and the way it attacks it is by using its lone pair of electrons. It grabs that proton, and what is required for that to happen, since a hydrogen can only have one bond to it, is that hydrogen-oxygen bond has to break, and the electrons in that bond go onto the oxygen here. And so as a result of that reaction, what we generate is BH, where the base, B, has formed a new covalent bond to the proton that it stole from the carboxylic acid. And then the other product of that reaction, the one that we're generally interested in, is the carboxylate salt, COO. And now that oxygen that lost the proton has a negative formal charge. So we have generated here what we call a carboxylic acid salt, or a carboxylate salt. And this reaction would have present within it, if we were doing this in real life, a counter ion, which would be a metal to counter the negative charge of the base. And that metal we would describe as a spectator ion because it's not changing throughout the chemical reaction, it's just along for the ride. It's M plus, or metal, with a positive formal charge at the start. And at the end, it's also hanging out as M plus. It's just that its partner at the beginning is the base. But after the base grabs a proton to become this neutral molecule, the base bonded to a proton, that metal then instead associates with the carboxylate salt to give the salt characteristic of an anion and a cation interacting. And this reaction that we see here, if the conditions of the reaction mixture are set up so that the pH is greater than about 4, then the reaction is going to favor the right side of the equation, the carboxylate salt. So in general, if the pH of a solution is greater than 4, particularly the more above 4 it is headed toward the side of basic, the more strongly this equilibrium is going to favor the right side of the equation. So if the pH is greater than 4, this side of the equation prevails. Meaning that if you were to look at what exact form a particular carboxylic acid molecule was in the body, if the pH is greater than 4, this form on the right is going to prevail. On the other hand, if you're in an acidic environment in the system, such as within the stomach, where the pH is certainly less than 4, then this side of the equilibrium prevails, meaning that we would have an abundance of the carboxylic acid molecule because at a low pH, there's an abundance of protons around. The way that we can think of it is as the pH increases, going toward the side of basic, there's a deficiency in the amount of protons available in the system overall, and so this proton from the carboxylic acid is lost to the base. On the other hand, if there's an excess of protons available in the system, meaning as the pH lowers, then we have plenty of protons available for this carboxylic acid to remain protonated. So let's take a look at some specific reactions where we can apply what we have looked at here. For example, let's envision that we are going to predict the product that results from the reaction of 2-methyl pentanoic acid reacting with lithium hydroxide, LiOH. I'll put this in as an equilibrium arrow here. We need to recognize first and foremost here that lithium hydroxide is a base, and the reason we recognize it as a base is that it has this hydroxy anion, or hydroxide ion, as we can call it here. We have OH minus, and that would be bonded to lithium plus through an ionic interaction here. Our lithium plus is Li plus and OH is OH minus because there's a huge electronegativity difference between those two atoms. Lithium is in the first column of the periodic table, oxygen is further toward the right side of the periodic table. With that large electronegativity difference, we expect that to be an ionic interaction. And now we can draw in our 2-methyl pentanoic acid. I'm going to draw in my group over here with my carboxy group so that I can show what's happening in the course of the reaction. Draw in my 5 carbons of my chain here, 1, 2, 3, 4, 5, and at position number 2, plug in my methyl group like so. And now what we will do to show how this is happening and what the product is, remember that the paradigm is that we take the base. In this case, we recognize that the base is the hydroxide anion. The base will have a negative formal charge on it. That base comes over, grabs a proton from our carboxylic acid. That forces the oxygen-hydrogen bond to break, and those electrons have to go somewhere. They go on to the electronegative oxygen atom because that electronegative oxygen is eager to take in those electrons from that broken bond. And then what results from that reaction will be, as our product, we will generate water, H2O, and I'm going to put that hydrogen that was picked up from the carboxylic acid in red here for emphasis. And then additionally to that water product, the product that we're probably more interested in, to be quite honest, is generally our organic product, and our organic product will still have its 5-carbon chain with the methyl group at position number 2 of that chain. And now at that oxygen atom that was originally the OH group, now we just have O with 3 sets of lone pair electrons. That's going to confer on that oxygen atom a negative formal charge. And then our counter ion here, we have to have a counter ion if we have an anion, will be lithium. So throughout lithium is again, and through all of these example problems that we will do here, we will describe lithium as a spectator ion, because in each case it's just along for the ride. Start off as Li+, it finishes the reaction as Li+. So with that, we have generated the product of deprotonating the carboxylic acid. Our product of deprotonating a carboxylic acid is the carboxylate salt. So I'll go ahead and label that as our carboxylate salt. The other way that we could look at this is we could classify, if you think back to your general chemistry, we could classify the carboxylic acid as our acid, and the acid, during the course of an acid-base reaction, gets deprotonated to become the conjugate base. So we would describe the carboxylate salt as the conjugate base in this reaction. And if we showed that the carboxylate salt were reacted with acids such as HCl, the reaction could go in the other direction because the presence of HCl acid would force the reaction to go back toward the side of the 3-methylpentanoic acid. So with this, we recognize that depending on the environment that a carboxylic acid is present in, if there is base present, then the carboxylic acid is going to react with that base to lose a proton and become the carboxylate salt. So when you're looking at chemical reactions, what you want to evaluate is when you see a carboxylic acid, ask yourself, is a base present? Because if a base is present, then what will happen is that carboxylic acid will very easily lose its proton, such that this equilibrium very, very much favors the carboxylate salt being the predominant major organic product of the reaction.